Hello everyone. My name is Natsue Abe from Mantle Promotion Office in JAMSTEC. Today, on behalf of the proponent, I would like to briefly introduce an ocean drilling project, M2m, that aim to drill into the oceanic Moho to mantle. And also, another proposal of Hawaii cluster drilling, a milestone proposal for M2m. So in order to submit these, these proposals, we had, we had 8 main international workshops since 2006, and the early stage of IODP in the program. And we already have about 90 proponents for these proposals, but still, more people's participation, new science, and new ideas are more than welcome. So please join us. The modern scientific ocean drilling started with the Moho project. The word Moho is a combined word, Moho and Ho. Can we see the pointer here? No. Okay. The word Moho is Moho and Ho. So I think this describes this project very well. Project proposed in 1985 by professors Harry Hess and Walter Munk. As you know, the Moho is the boundary between the Earth's crust and mantle. So they found by the Professor Andrea Mohorovic. So the same picture is on the T-shirt of Colbert because he's from Croatia, same country from the Mohorovic. Anyway, so as you know, the Moho is the boundary between the Earth's crust and mantle, and it is ubiquitous everywhere on Earth. And the Moho is the outermost boundary. The outermost boundary, the Earth's interior, but yet has been directly investigated. So they thought it was the technically feasible to penetrate in the oceanic crust, which is relatively thin compared to the thick continental crust. They also thought that it has the same impact as space exploration. This was the beginning of the Moho project. So in 1961, the project Moho started. The ship CAS-1 spotted in offshore Baja California and penetrated 183-meter sediments and 40-meter crust and at the 3,500-meter water depth. This was the first drilling in the oceanic crust, and it took basalt samples from the seafloor. At that time, the participants received a personal congratulatory letter from President Kennedy. However, in 1966, the US Congress issued the official cease orders. And since then, at that time, the frontier is beyond the availability of the technology of at that time. Since then, the penetration of Moho has been a symbolic goal for many geoscience over 4 decades. But 40 years later, during research, GQ was built and it would become feasible. There were some discoveries along with the original Moho project. For example, two rock types, peridotite and eclogite, were considered as the component of the uppermost mantle at that time. During site survey of the Moho project, of Hawaii and of Baja California, Harry Hess found the strong anisotropy of the seismic velocity in the uppermost mantle. Such strong anisotropy can't be made by the eclogite because it is quite isotropic. But olivine, the main component of peridotite, does. After this, Lingwood and Green, 1966, demonstrated by high-pressure experiment, and that shows the oceanic Moho is much shallower than the pressure of the phase transition between gabbro and eclogite. Then the peridotite upper mantle was confirmed. Here is the history of scientific ocean drilling. It started with the Moho project in 1961. After stopping Moho project in 1968, DSDP, Deep Sea Drilling Project, started in the US. Japan joined DSDP in 1975. In 1983, Ocean Drilling Program with 21 member countries was started, that is international program. In 1985, Georges resolution, vessel Georges resolution start the operation. In 2005, IODP, Integrated Ocean Drilling Program, was started with 25 member countries. In 2005, Drill Research CQ start operation. In the 2013, the Phase 2 IODP, International Ocean Discovery Program started. And now we are in the final stage of Phase 2, IODP Phase 2. And from 2024, the scientific ocean drilling will open a new door. The science community developed the new science framework until 2050 within the new framework. So, and also, before IODP started, a couple of big workshops to initiate IODP called Concord and Complex. And during the workshop, people set a certain target to drill into the mantle. The status quo in scientific ocean drilling, we had drilled only 2 kilometers into the oceanic crust, which is only 1/3 of the Moho depth. And not much crustal drilling has been done compared to the sediment drilling. We have reached only the thin skin of the solid earth. And then here, drill vessel GQ counts. And the science community submitted Moho to mantle M2m proposal to IODP in 2012. So next, I briefly introduce the M2m proposal. By drilling intersection of oceanic crust and upper mantle, we set 10 fundamental questions and hypotheses to be tested. Specific objectives include the next 4 science targets: reach and sample return from the in situ mantle, nature of geological Moho, the formation and evolution of the oceanic crust, and the limits of life. The highest priority is sample return from the mantle, in situ mantle. So we can obtain the peridotite samples like mantle generis included in basalt lava, or mantle section of the ophiolite, or serpentinized abyssal peridotite on the seafloor. And we also can estimate the chemical composition of the mantle from basaltic magma of mantle origin. However, they are not the in situ mantle samples. So we do not know the exact volatile content in the mantle. For example, carbon and water are estimated to be 0.7 weight percent and 0.002 weight percent respectively of the whole Earth's composition from the surface samples. And however, while the amount of estimated from C1 chondrite are 3.2% and 2 weight percent respectively. What caused this difference? So the second target is the geological nature of Moho. The Moho is ubiquitous on Earth, and it has about 6-kilometer average thickness in the oceanic crust. And Moho is the outermost significant boundary between the crust and mantle, which is defined as the velocity, density differences of the mantle and crust. That means the physical properties are largely different from the crust and mantle, but we do not know the geology there. And for example, a sharp Moho is observed in the one-dimension velocity structure of the Western Pacific using a borehole seismometer, like this. On the other hand, in the bend fault zone just before subduction into the Japan Trench, this is a two-dimensional image, and here at the bend fault, the velocity jump at Moho is found to be smaller. And significantly reduced the velocity in the crust and mantle. This is probably due to the reaction between the oceanic plate and seawater, causing serpentinization in the uppermost mantle, but such changes are observed only in very limited areas. In order to obtain the ground truth to endorse such physical observation, Moho should be penetrated. But the reality is, we haven't even penetrated the boundary between the upper and lower crust yet. The hole 504b is the deepest hole in the ocean crust that penetrated the layer 2-3 boundary, but did not sample gabbro layer. Whereas hole 1250d has sampled gabbro, but not penetrated the layer 2-3 boundary yet. Further drilling is needed to understand the petrological meaning even at the layer 2-3 boundary. The third objective is the formation of the oceanic crust and the mode of accretion of the crust. This is related to the second objective. On an annual average basis, the mid-oceanic ridge produce the majority of the basalt magma on the Earth's surface. This means mid-oceanic ridge release an overwhelming amount of heat and also element from Earth's interior compared to other regions. Because we haven't got continuous drill hole in the oceanic crust. We do not know the detailed structure of the oceanic crust yet. There is two end-member models of oceanic crust accretion. One is Gabbro Glacier model, the other is Seed Seal model. In the Gabbro Glacier model, there is a big magma chamber in the lower crust. And in this magma chamber, the magma crystallizes on the top of the chamber and precipitate the crystal and accumulate the crystal here and may form the lower crust. And on the other hand, there is small melt length near the Moho in the seed cell model, which rises up gradually due to buoyancy, intruded as a cell and form the lower crust. So between the two models, of course, the thermal gradients are different. In the Gabbro Glacier model, the thermal gradient is greater in the shallow part because we have the hot magma chamber here, and the hydrothermal activity is only occurred at the shallow part. The seawater cannot penetrate in deep. On the other hand, in the seed seal model, the seawater can penetrate to deep because the thermal gradient is small and the hydrothermal activities could be occurred throughout the lower crust. So that's so different. And again, I want to emphasize the Moho is the only boundary to reach and observe and describe the in situ melt migration system. The last scientific objective is the limit and the control factors of the seafloor biosphere. So Shino-san and Inagaki-san already talked about this a lot, and I don't have much words to saying this. But again, if we have water, the circulating water, and the temperature is low enough, possibly we have the biosphere there. So now, where we should drill into the mantle for the first time? Even just about 20% of the modern ridge and the fast spreading, that makes about 50% of the present-day ocean floor. And the fast spreading ridge formed such majority of the ocean floor, and that is circulate the recycled into the mantle over past 200 million years. And detailed seismic exploration revealed so far the complex structure in the slow-spreading ridge, slow-spreading lithosphere like Indian Ocean or the Mid-Atlantic Ocean, oceanic ridge, or the Antarctic Ocean. And on the other hand, the fast-spreading ridge and fast-spreading lithosphere is relatively simple and very homogeneous. So, now we decided the very first hole into the mantle should be penetrated in the fast-spreading oceanic plate, that is in the Pacific Ocean. And where in the vast Pacific Ocean can we drill into the mantle? The criteria for achieving the scientific objectives are typical or normal oceanic crust and a relatively simple tectonic setting that is approximately 6 kilometers thick and clear Moho discontinuity. The realistic technological development constraints, the water depth is about 4,000 meters and total drilling length of shorter than 12,000 meters, and temperatures is lower than 250 degrees Celsius. In addition, taking into account the logistic and some kind of housekeeping stuff, the site should not be too far from major port or not too far from a heliport within about 300 kilometers. And we need calm sea conditions and in the blue ocean or within the EEZ of an IODP member country. And above all, where the detailed site survey can be done. So not too far from the the land or the rough water is difficult to penetrate. They thoroughly considered all these conditions. We decided the three site candidates. In the Cocos Strait, off Hawaii, and off Baja California. All of them have pros and cons. And none of them meets all scientific criteria and technical constraints. But those three sites have relatively shallow water depth and low temperature at Moho, more site survey data, logistically reachable, and simple tectonics compared to any other places on Earth. So this table shows the principal characteristics of the three sites. Again, each site has pros and cons. And now, I can't explain the technology because I'm not an engineer and I don't know much about it. But for 10 years already, and also last year, engineers have been in conducted feasibility studies for drill to this mantle drilling, and the report has been properly published. So if you are interested in, please search Google these feasibility study reports. And the feasibility study, for example, estimate drill rate based on the coring strategy or casing strategy, and the rough estimated rough assumed rock physical properties at each potential site. And the estimate suggested the number of days required in them and from the drill rate, including considering all the appropriate drill bit. As a result, we know that it will take 202 days at the shortest and 368 days at the longest, and about 1 year from the start drilling to reach the mantle. Thus, the study reports that mantle drilling is feasible. However, it's not been budgeted yet, and it will take some time to realize the project. And also, we need to develop technology such as the slightly deeper and the combination of these technology elements. Meanwhile, to determine the location of the 6-kilometer main hole drilling, we first conducted a site survey offshore Hawaii in 2017. Based on this, international workshops were held in 2018 and 2020 to discuss further drilling proposals. And the proposal was submitted for cluster drilling to 2,500 meters below seafloor. That is penetrate the upper and lower crust boundary with the Professor Susumu Umino as PI. The full proposal was submitted. Yes. So, at the last of my presentation, I'd like to introduce a word of Professor Harry Hess as the original Moho project. Perhaps it is true that we won't find out as much about the Earth's interior from one hole as we hope. To those who raise that objection, I said, if there is not a first hole, there cannot be a second or the 10th or the 100th hole. We must make beginning. So we have to start, otherwise we cannot know anything about the Earth's interior. Okay, thank you very much for kind attention.